Okay, here again is our solution when the discriminant is less than 0. We can reduce the solution to this, where omega is simply the square root of the negative of this term. Omega being interpreted as the angular frequency of an oscillation. I'm going to wave my hands a little bit because we've so recently done this. This implies a real behavior equal e to the negative gamma over m times t multiplied by an alpha cosine of omega t plus phi. Using this notation similar to what I did before. Now, this isn't really equal to this, but if we choose our A and B properly, we can make it equal to this. So this is a valid solution to the equation, and it turns out to be a valid general solution to the real behavior of this system. Now, our e to the negative gamma over mt has a graph. Looks like this. It's just a decaying exponential, e to the negative gamma over mt. Decaying exponential. Again, this is a graph of x versus t. Our graph of alpha cosine of omega t plus phi is just a cosine function or sine function. It's just an oscillatory function. By choosing phi and a, we can start at any point on the vertical axis with any phase, so that this might just look something like this. Where the period of the function from here to here is just 2 pi over omega. Of course, this axis being the t, that means that our period of the function will be 2 pi over omega measured in units of time. Our x of t function is going to be the product of a function of this nature and a function of this nature. Now this should be something that you learned in pre-calculus and reinforced in calculus. We have a decaying exponential, and we have some alpha that could be brought out in front, so this graph could be, and as a matter of fact, let's back up just a second, and let's just take this alpha and put it over here. We haven't labeled a scale on either of these axes, so that's a perfectly legitimate thing to do. And then this function is just going to be our cosine of omega t plus phi. Now we take our graph of the exponential here, and I'm going to spread it out a little bit more. And we also draw the negative of the exponential for reasons that will become apparent in a minute. When we multiply the values of this function by the values of this function, because of course this function is multiplied by this function, we end up with an oscillatory function that has the same period as this one, but which oscillates between the two exponential curves. Now the graph I've drawn here would correspond to a pendulum being released to the right of our equilibrium position, but not simply released, given a push in this direction so that it moves further from the equilibrium position before beginning to swing back toward equilibrium. So the pendulum is going to move out, and then it's going to come back to equilibrium, and then it's going to swing past equilibrium, but not as far as it did here. So it's going to swing a little ways past equilibrium, then it's going to come back to equilibrium and come a little ways past equilibrium again, but not as far as it did before swinging back. And what we have is a pendulum whose motion kind of goes like this: out to here, back to here, out to here, back to here. And it's going to continue that similar pattern, gradually decaying. The amplitude of its motion continually decreasing, approaching zero. So the pendulum will approach the equilibrium position by oscillating closer and closer and closer to the equilibrium line. Much more can be said. For example, the smaller the value of gamma or the larger the value of m, the smaller the half-life of the exponential. In other words, if you don't have a lot of drag, this thing will go on for a long time, decaying very slowly, because this coefficient of t is going to be small. If you have a lot of drag and or a small mass, then this coefficient is going to be large. You're going to have a quick decay. And the values of g and L will affect the value of omega, and any solution we come up with should match the expected reality of the system we're trying to model. Again, that's an art and a science. There are a lot of details to work through before we get to the level where we can really intuitively interpret these solutions, but this should serve as a beginning.